In this video, we're going to solve exponential equations. We'll do two examples. One for exponential growth, we'll do another one for exponential decay. The processes are the same, the steps we take. I've written up here A equal to A, see that sub-zero? We can call that A naught. A equal to A naught times e to the RT. R represents the rate. This A naught is the beginning amount, and this A is the final amount. And for our first example, let's say there's a country in 2012 has 129 million people. And we want to estimate how long it will take before this population reaches 150 million. If it has a continuous growth rate of 1.2%. So the first thing, how do you write 1.2% in an equation? We write that as 0.012, correct? That's equivalent. 0.012 is 1.2%. So let's start plugging the numbers in. 150, final amount, equals 129, beginning amount, times e to the 0.012t. Now I didn't write down the millions. I could have, but if I have 150 million on this side, 129 million on this side, I can divide a million on both sides of the equation. And these numbers are a lot easier to work with. Alright? So that's why I'm just going to use 150 and 129. Now the first step, we need to isolate this e. We need to isolate this expression here, this e to the 0.012t. So we'll divide 129 on both sides. That's step one. Make sure it's isolated. So I have 150 over 129 equals e to the 0.012t. Step two, we're trying to solve for this little t up here in the exponent. We're going to take the natural log of both sides. So we'll take the natural log of 150 over 129 equals the natural log of e to the 0.012t. We did that for a reason. This t was up in the air, up in the exponent, and now we can use the property of logs. It allows us to take this exponent and move it in front of that logarithm. So this right side is going to get really neat in a second. We can rewrite this as 0.012t times ln of e. Yeah. Leave this left side, ln 150 over 129. Now, I want to be careful too as you're going through this. Don't round that number. If you hit that and find that in the calculator and you round that decimal, it can really round off the final answer. So that's why I'm writing it as 150 over 129. Now the natural log of e is a 1 because this base right here is an e. So this ln of e is 1. I can just take that off. And I have ln of 150 over 129. And we have one more step. Let's divide 0.012 on both sides of the equation. And when I divide that, t equals ln of 150 over 129 all over 0.012. And I'll hit that on a calculator. So we get the natural log of 150 divided by 129 divided by 0.012. And it comes out to be about 12.56 years. Alright? 12.56 years. That's an estimate. So I'll take my equal sign and squiggle it, right? Now some students like to use a shortcut, and that's fine, because all these problems work the same, and this final expression right here, they make a formula out of that. T will always equal the natural log of the final amount divided by the initial amount divided by the rate. I'll write that over here. I'll leave this up here. T equals ln of A over A naught all over the rate. So please feel free to use that if you want. Let's do one more problem. This time, let's use this type of same process. It's the same process, but let's solve an exponential decay problem. All right. Let's see. We're going to do carbon dating. Carbon 14. Carbon 14, everyone, this isotope, it has a decay rate of negative 0.000121. So I'm going to rewrite this equation. Let's say that was given to you. e to the negative 0.000121. All right, this is for carbon-14. Yeah, the half-life is about 5,700 years for carbon-14. That's how long it takes for it to reduce to or decay to half its original amount. And this is a dating method that's used to date artifacts. So let's say an artifact was discovered by some archaeologists. And scientists took it back to the lab, and they realized there was 81% carbon-14 remaining in that artifact that they discovered. Okay? And we're going to estimate the age of this artifact. So what do we do? Well, didn't it originally have 100%? So right here, the beginning amount, yeah, it had 100%, or 1.0. When we found it, it had 81%, which is 0.81. There you go. Initial amount, 100%. Final amount, 81%. I guess another way we could have looked at this is, there was 81% of the initial, and then the initial. And you'll realize you'll come right to here, because you can divide that A naught on both sides of the equations. So there's two ways to look at this problem, but eventually we're going to get to this 0.81 equals 1 times e to the negative 0.001212. Alright, now, everyone, that means I don't have to put that 1 there. The e is isolated. We're going to solve this like the last problem. Take the ln of both sides. Natural log of 0.81 equals the natural log of e to the negative 0.0001212. Next step, I can now move this to the front. Boom. 0.00121t times ln of e equals the natural log of 0.81. ln of e is 1, so I can remove that. Bye-bye. And your last step, divide this number on both sides. So t equals the natural log of 0.81 divided by negative 0.000121. And I'll hit that on the calculator. So the natural log of 0.81 divided by negative 0.000121 comes out to be about 1,741 years. All right, 1,741 years ago. All right, that's when that artifact was placed there. That's the age of this artifact, right? Yeah, and keep in mind, you still could have used this as a shortcut, right? Your little formula. You would have done ln of this number over this number. And you notice you would have had what? 0.81 over a 1. You would have had this. So you might have done a shortcut just to get to this step right here, which is fine. That's totally fine. But I think, seeing this process really, really helps you retain or remember a formula like that. That's why I showed it. And that's it.